we've got sine to the sixth of x times cosine to the third of x dx. All right, so I'm a little disheartened because these trig functions are raised to really high powers, and not only that, but our discussion on strategies had to do with trig functions raised to even powers, trig functions raised to odd powers separately. Here we've got one of each. Now, it turns out that in the long run, it's a little bit easier to deal with odd powers. So if I have trig functions where I've got one raised to an even and one to an odd, I'm going to pick that odd one and focus on the odd power. So focus on the odd power, if possible. Now, our strategy, or our technique for working with these odd powers is, let's pull one of those cosines off to the side and use that as our canceling for our derivative of our u. So I'm going to immediately rewrite this as the integral of sine to the sixth of x times cosine squared x times cosine of x dx. And this last cosine here is the one that I want to cancel with my derivative. All right, so what should my u be in order to cancel a cosine? Yeah, a good choice would be, let's let u be equal to sine x. So then our derivative, du over dx, is cosine x, and that's good, that's what we were looking for. And so dx is equal to du over cosine x. Okay, so we get back over here to our integral, and we can start to do some substitutions. Here, the u actually shows up in our problem. Sine of x, quantity raised to the sixth, becomes u to the sixth. We have a cosine squared x. Another cosine x, and our dx is du over cosine x. So life is good in terms of canceling our cosine x, our individual singleton there. And all that we have left is an even number of cosines. And if I have an even number of cosines, and my u is sine, I can use that tattooed identity on my arm right here. Sine squared x plus cosine squared x equals 1. So that means that cosine squared x must be 1 minus sine squared x. And our sine was our u, so that's 1 minus u squared. So we end up with the integral of u to the sixth. This cosine squared x is 1 minus u squared, and then we have a du at the end. Something you might notice about these integrals, especially u substitutions, is that there's always this side work that goes along with it. My first calculus teacher would call this the salad bar off to the side. So anyway, so there's always some salad bar work to be done. Okay, so we now have everything in terms of u. Are there any questions up until this point? So we identified an odd power, pulled one of those odd powers off to the side to use to cancel with our derivative, made a good choice for the u, so its derivative canceled that cosine. And from there, we could use our trig identity to get everything in terms of u's. Everything's in terms of u's. I'm not ready to take an antiderivative because there's multiplication going on here. So I first need to distribute this u to the sixth through. So I end up with u to the sixth minus u to the eighth, and a du at the end. Finally, I'm ready for some calculus. Here's where the antiderivative comes in. U to the seventh over 7 minus u to the ninth over 9 plus c, turn back into x's. have sine to the 7th of x over 7 minus sine to the 9th of x over 9, all of that plus. Yes?
Knowing that your u is sine, instead of changing cosine into 1 minus u squared, can you actually just take away the power and like make it equivalent to 1, since sine squared plus cosine squared is equal to 1? Can't you take the cosine squared, take off 2 powers from the u?
Here.
Yeah.
Oh, so make this u to the 4th?
Yeah.
And then, so the problem is that these are multiplied together as opposed to being added together.
Okay. But if they were added together, you could.
If they were added together and you saw a sine squared plus a cosine squared as part of the problem, then you could change that into a 1 right away. Yeah. Okay, other questions? All right.
Why do the typically with problems like this with those even powers, it really trips up the computers that solve these types of problems to where you get typically like long regressions.
Okay.
Why does that always happen?
That's a good question. In terms of the computer trying to do this numerically?
Because obviously those identities are pre-programmed to some extent, whether a device like this or Wolfram Alpha or whatever.
And I think part of the problem is that there is some sort of human cleverness that goes into visually identifying when can we make these replacements. I mean, certainly like something like this, it is pre-programmed in almost anything, but there are so many identities that it's a pattern recognition thing, and humans are often better at pattern recognition than computers. Yes?
I don't know if I'm jumping the gun or not, but what if you have 2 odd powers?
If you have 2 odd powers, then you're totally in luck. I mean, let's say that we made this 61. So now you've got an odd power up there. The only difference would be that this particular, you could choose either one to pull the trig function out of in that case. You'd have, either choice would work for you.
Okay.
And life would be good.
Okay. Thanks.
Yes?
Did you use the power reducing one on that like a lot of times on sine to the 6th? Like did you use that a few times?
If you did not have, if you just had sine to the 6th,
Oh, okay, got it.
then you would use that power
Because
reducing
you have that
formula.
odd stick on and
That's right. Okay. So, our final example for today is a particular antiderivative that you probably wish you knew in Calc 1, and you were really disappointed to realize that I have no idea what this antiderivative is. Okay, final example of today. The integral of tangent of x dx. All right, I mean, this is a really easy one, right? I mean, tangent of x, we know what the derivative is, it's secant squared x. But I don't know any function off the top of my head whose derivative is tangent x.
Could you just say it's sine over cosine?
So this seems like a really good idea. So what is tangent of x? Well, trig identities, tangent of x is sine of x over cosine x. And so now I've got something where I've got trig functions here, and I want to make a choice, because I'm going to make a choice for u where the derivative of my choice is going to cancel one of the trig functions. So think about this for a second. In order to cancel my derivative over here, I need something that's in the top. And so I need a choice for u whose derivative will cancel sine x. So a good choice for u might be, let's let u be equal to cosine x. So if I choose u to be cosine x, then my derivative is negative sine x. And I can solve and get dx is equal to du over negative sine x. And this is going to work out really well, because I've got sine x over u, dx is equal to du over negative sine x. so by making this choice for u, the signs will cancel. The negative sign, SIGN, can get pulled into the front. And so we've got negative the integral of 1 over u du. If I had chosen my u to be sine of x, then we would have had cosines both in the denominator. They would not have canceled each other. All right, so we've got negative the integral of 1 over u du. Any questions about that so far? Good. So take a look at your neighbor and remind your neighbor what the antiderivative of 1 over u is.
Yeah, natural log of u.
Natural log of u.
All right.
Naturally.
I've heard several people say this, so I'll just write it down. Natural log of u. Do I need to remember anything else?
Absolute value of u.
Yeah, these guys have to be absolute values. Why? Well, because we didn't necessarily know that whether u was positive or negative in the original problem, and natural log only has positive inputs. Okay, so we have negative natural log of the absolute value of u plus c. And so I turn this back into my x's, and we have negative the natural log of the absolute value of cosine x plus c. So what this says, and this is a really good integral to just remember so that you never have to rederive this one again. The antiderivative of tangent x dx is negative the natural log of the absolute value of cosine of x plus c. Now, before you box that off and call it a day, if you happen to check inside your textbook, and you look this one up in the front page or the back page of the textbook, you'll notice this is not exactly what they have in the textbook. So in the textbook, what they've done is, remember that there's properties about natural logs. If you have a constant in the front, you can bring it inside the parentheses, or inside the absolute values in this case, and it becomes a power. And so this is the same as the natural log of the absolute value of cosine of x raised to the negative 1 plus c. This is not an inverse negative 1, this is a reciprocal negative 1. And so this means this is the same as natural log of the absolute value of 1 over cosine x plus c. What is the reciprocal of cosine? Yeah, that's secant. And so this is natural log of the absolute value of secant of x plus c. And so if you choose to memorize this particular antiderivative, the most common way to see it is that the antiderivative of tangent x is natural log of the absolute value of secant x plus c.
So they just simplify it as far as the figures they can do it.
That's right. That's
But
right.
that answer would be correct.
This top one is also absolutely correct as well. Okay, any questions or comments about this? So what we've talked about today is a little bit of material out of 6.2. I'd hope to introduce you to 6.1 today, but we didn't quite get there, so we will start that on Wednesday. So practice problems for tonight are out of